Today, we're diving into one of the biggest stories in modern tech, the incredible leap that changed how AI understands language. We're talking about the jump from an older, slower way of thinking to the absolute powerhouse architecture that makes the AI we use every single day possible. Let's get into it.
So it really all boils down to this one simple sounding question. How do you get an AI to read a really long book and actually remember what happened in chapter 1 by the time it gets to the final page? I mean, for years, this whole challenge of long-term memory was a massive roadblock for AI.
The heart of the problem is just how you deal with information that comes in a sequence. Language is a perfect example, right? It's just one word after another. And to get the real meaning, you have to remember what came before. For a long, long time, the most obvious approach was to just, copy us. Teach it to read one word at a time. And that idea brought us to the first major player in our story, the Recurrent Neural Network, or RNN. Probably the best way to think about an RNN is that it's reading a sentence through a tiny little peephole. It looks at the first word, gets a little piece of information, then slides the peephole over to the next word, all while trying to remember what it just saw. And that little bit of memory it's holding on to, that's called the hidden state. So the process is pretty straightforward. The RNN reads word number 1 and creates a memory. Then it reads word number 2, but it uses the memory from word 1 to understand it. And it just keeps doing this, step by step, all the way down the line. It seems totally logical, right? But it has a massive, fundamental flaw. And that flaw is its memory. It's just not very good. As the sentence or the paragraph gets longer and longer, that memory of the first few words starts to get really fuzzy. There's a technical term for it, the vanishing gradient, but the bottom line is this. By the time the RNN gets to the end of a long text, its memory of the beginning is so faint, it might as well be gone. It just can't hold on to those important connections over long distances. So the entire field was kind of stuck. It turns out the answer wasn't to just give the AI a better memory. Nope. The answer was to give it a completely new way of reading altogether. It was a true paradigm shift. Then in 2017, a paper drops with this incredibly bold title. I mean, talk about confidence. It introduced the world to something called the transformer architecture. And it changed everything. The core idea was revolutionary. Stop reading through a tiny peephole. Instead, look at the entire sentence all at once. This magic is possible because of a brilliant innovation called self-attention. What it does is let the model see every single word at the same time, and this is the crucial part, figure out how important each word is to every other word. So in a sentence like, the boy who is hungry is eating the right banana, it can instantly connect eating directly to boy and banana, no matter how far apart they are. It just knows what matters. So let's just put this side by side, because this is the key. RNNs are stuck processing things sequentially, one after another. Transformers do it all in parallel, bam, all at once. This jump from recurrence to self-attention wasn't just an improvement, it was a total revolution. And it came with an absolutely massive side effect. That side effect? Scale. Because transformers can process all those words in parallel, you can suddenly train them on a scale that was just impossible before. This is what unlocked the door to using truly gigantic datasets, and it led us directly into the era of the large language model. And you can see the impact on training speed right here. It's staggering. An RNA is just slow by its very nature because of that step-by-step process. But with the Transformers parallel design, we can throw huge amounts of computing power at it all at once, which makes training dramatically faster and lets us build these incredible models with billions of parameters. This table really sums up the key differences. Transformers are amazing at those long-range dependencies, remembering chapter 1. But look at that last row, pre-training. Because they're so fast to train, you can have them read like the whole internet before you give them a specific job. They learn grammar, facts, and reasoning ahead of time. Trying that with a slow-moving RNN was just way too hard, which really limited what they could do. And what did this whole revolution give us? Well, how about models you've definitely heard of? GPT? That T at the end literally stands for transformer. BERT, another game-changing model, is also built on this exact same architecture. These are the models that blew the doors off what AI could do with language, and it's all thanks to that core idea of parallel self-attention. But hold on, does this mean RNNs are totally obsolete? Just a relic of the past? Well, not quite. As with any tech, the full story is a little more nuanced. It's less about one being better and more about them being different tools for different jobs. So here's the takeaway. Transformers are like having a satellite view. They're perfect for seeing the whole picture and understanding broad context, like summarizing a huge document. But RNNs, which go step by step, like following a trail of breadcrumbs, can still be super valuable. Think about analyzing something like real-time stock market data, where the exact sequence of events is absolutely everything. In a case like that, the old-school RNN might still be the right tool for the job. So we went from reading one word at a time to seeing the entire picture instantly. That single leap from sequential to parallel processing is what defined the entire last era of AI. And it leaves us with a pretty fascinating thought, doesn't it? What's the next breakthrough going to look like? What comes after seeing the whole picture?